Hello, hello, and welcome back to CS422 Theory of Computation. We have completed our chapter 4 on structural complexity, where structural here means with respect to notions of reduction. Specifically, we considered polynomial reduction as a means in order to compare the computational complexity of problems whose absolute, whose resource-bounded complexity is unknown. So structural complexity is kind of a complement to resource-bounded complexity, where resource-bounded complexity means we consider how many resources a certain decision problem needs and suffices in order to be solved algorithmically. For example, polynomial time. Time is a resource. Or exponential time. Time, again, a resource. These are resource bounded complexity class. Or polynomial space. Space here meaning memory. So polynomial space is a resource bounded defined complexity class. And as opposed to that, are complexity classes that are defined by comparison to reference problems, that is, problems that are defined to be, for example, polynomial time equivalent with respect to polynomial time reduction equivalent to, for example, Boolean satisfiability. So as according to Cook-Levin theorem, this structural complexity class NP can be characterized in this way, or as we characterized it in the syntactical way with this existential quantifier over a witness, or we also characterize it in terms of while plus programs that are able to use guessing with the strange semantics of guessing, not random guesses, but whenever there exists a suitable sequence of guesses. So that's structural complexity as opposed to and complementing resource-bounded complexity. And today we're continuing or resuming our discussion of resource-bounded complexity, namely with the complexity class PSPACE, the class of problems that can be designed using a polynomial amount of memory. And we're going to look at this class again also from the structural perspective, namely with respect to the notion of polynomial time reduction that we discussed in the last chapter. So let us start the slides. So here we're going to discuss the complexity class PSPACE, and we're going to discuss the polynomial hierarchy. So the polynomial hierarchy is kind of a resource-bounded counterpart to the analytic hierarchy that we discussed with respect to computability. And as polynomial time reduction is a resource-bounded counterpart to computable reduction, the polynomial hierarchy is a resource-bounded counterpart to the analytic hierarchy. But we're going to get there later in this chapter 5. So let's start with chapter 5 with an overview. In this chapter, we're going to introduce some problems that we then will locate to belong to this complexity class PSPACE, namely quantified Boolean formula, 3 quantified Boolean formula, and a certain game on two-player game on graphs. And we show that these decision problems can be solved using a polynomial amount of memory. And we'll see why or that we cannot prove these problems to not only not be decidable in polynomial time. We've had many problems in this class of this type, but also we will see why we cannot show these problems to lie even in the class NP. Remember, NP is this smaller class according to our small hierarchy, starting with P, then NP, then PSPACE, and finally exponential time. So these problems are not even known to lie in the complexity class NP, but we'll show that they belong to the complexity class PSPACE. And then we're going to apply polynomial time reduction to show that these problems are actually complete, that these hardest problems for this complexity class. Then we'll reconsider the question that we discussed in chapter 4, whether NP and co-NP are different or equal. Remember, if P is equal to NP, then also co-NP is equal to NP. But if P is different from NP, then there may be either two different classes, NP and co-NP, or they may coincide, or they may have a common intersection but still be different. And so this is an unknown problem about these complexity classes. And we're going to look at a similar question regarding the complexity class PSPACE and its complementary counterpart co-PSPACE. And we're going to see not only are these equal, but they are actually equal to n-PSPACE, the non-deterministic polynomial space. This is Walter-Savage's theorem. And then we're going to look at the polynomial hierarchy, which is a hierarchy inside the complexity class PSPACE, kind of a counterpart, resource-bounded counterpart to the analytic hierarchy that we discussed in the chapter on computability theory. And again, we're going to take two perspectives on this hierarchy. First, a syntactic one defined in terms of alternating quantifiers and the number of alternating quantifiers. And secondly, but equivalently defined semantically in terms of certain variants of a while plus program. And finally, we're going to approach the question whether P is equal to NP from the perspective of oracle computation. So the polynomial hierarchy, the semantic version will be defined in terms of certain oracles. And the famous Baker, Gill, and Soloway theorem shows that with respect to some oracles, actually P is equal to NP, and with respect to other oracles, P is different from NP, which means that many proof techniques cannot help solve the P versus NP problem, namely any proof technique that also can deal with oracles, and that turns out to be most proof techniques. So that is a very famous and important meta theorem, if you like, that shows that certain proof or approaches to P versus NP won't work. So that's our plan, and let's start with this new decision problem, QBF, which is short for quantified Boolean formula of quantified Boolean expression. As you recall, Boolean satisfiability is kind of an existential Boolean formula problem, namely the question whether there exists an assignment that makes a Boolean expression true. And here we generalize that. We not only allow the existential quantifier, but also universal quantifiers and combinations of both. So this is the recall of the Boolean satisfiability problem. Given a Boolean term, does there exist an assignment? So here we have n quantifiers, as many as their variables, that make the expression evaluate to 1, evaluate to true. And the generalization is given a Boolean term with, now we have m variables. Does the following hold? There exists an assignment for the first variable, so that for all assignments of the second variable, there exists an assignment to the third for all, and so on, until all variables have been quantified over. So yeah, that seems like an artificial question, to be fair, and doesn't even look like a generalization of the Boolean satisfiability problem. But to see that it actually is a generalization, consider or suppose that here we have artificially inserted Boolean variables with even index y2, y4. So all the variables that are quantified universally over here. Let's just suppose or consider the case where these have been introduced artificially and the variables don't even occur. Or put differently, let's take this existentially quantified expression and let's artificially insert new variables like z1 up to zn that do not even occur in the Boolean formula phi, and we add universal quantifiers over these new variables z1 up to zn. Then, of course, these new quantifiers do not affect at all the truth, the validity of such a statement, because the variables don't occur here. And now the thus additional quantified Boolean expression with additional universal quantifiers is of this very form and still equivalent to this. So that demonstrates that quantified Boolean formula indeed includes and just generalizes the satisfiability one. That means that quantified Boolean formula as a decision problem, 0, 1, yes, no, must be at least as hard as Boolean satisfiability, which is NP complete. So here we have a problem which must be at least as difficult, and the question is it at most as difficult, or is it strictly more difficult, right? And we're going to approach that question using the notion of polynomial time reduction that we discussed previously. So does this belong to NP or not? This is the question. Also observe that quantified Boolean formula also includes a co-NP complete problem, right? So it includes, as we just explained, the NP complete Boolean satisfiability problem, right? By artificially introducing new dummy variables and universal quantifiers alternating, right? In every second place. But it also includes the co-NP complete unsatisfiability problem, where unsatisfiability is the question given a Boolean expression. Is it true that for all assignments the expression evaluates to 0? So this is the complement, the negation of satisfiability. Not being satisfiable means that for all assignments the Boolean expression evaluates to 0, to false. And again, also this co-NP complete problem is included in QBF. Namely, recall that this problem asks for all assignments, for all y1, for all y2, and so on, for all yn. Is it true that the Boolean expression evaluates to 0? Well, whether we say it evaluates to 0 or whether we ask whether it evaluates to 1 makes no difference. We can just take the negation of the Boolean expression, right? So this evaluates to 1 if and only if its negation evaluates to 0. So what it evaluates to doesn't really matter at this stage, since we don't require conjunctive normal form anymore, right? So the negation of conjunctive normal form, of course, is not in conjunctive normal form. But since here we consider general Boolean terms without restricting to conjunctive normal form, these evaluate to anything we like. Yeah. So, and yes, as I said, unsatisfiability is complete for co-NP and expressed with this universal quantifiers for all y1, for all y2, for all yn. Does it evaluate to still, let's say, 1? And then we can play the same game again, introduce artificially new dummy variable z1 to zn and have quantify over them now existentially, and thus we can also express unsatisfiability, which is co-NP complete, as a special case of QBF, or quantified Boolean formula, so that this decision problem also includes the co-NP complete problem. So, and since if you believe that NP is different from co-NP, then kind of the union of both, right? Which in the is kind of even larger. So we can really expect that this quantified Boolean formula problem should be strictly harder. It must be at least as hard as NP and at least as hard as co-NP. And actually, there's an entire hierarchy. So next, let's observe that this decision problem can be solved in polynomial space in a polynomial amount of memory. And to this end, let's design an algorithm that solves this problem using a polynomial amount of memory. And it's turns out to be a recursive algorithm. So here we consider an algorithm that recursively evaluates or determines the truth of this quantified expression such that the memory consumption of this algorithm satisfies the following recurrence. So it has the parameter m, the number of variables, is the amount of memory used to solve the m-1 variable problem, plus some polynomial overhead, polynomial in the binary length. Oh, and yeah, I need to emphasize something in detail here, right? So when we say these are alternating quantifiers, y1, y2, y3 exists for all, exists for all. Right, so the first remark I'd like to make is that this is not really a loss of generality to force an alternation, because if maybe there are two existential quantifiers in an expression, then using the dummy variable technique that we've mentioned several times already, we can always introduce and force an additional universal quantifier over a dummy variable, which is not really, which does not really occur in the Boolean expression at all, and thus introducing these additional dummy quantifiers in order to force the quantifiers to alternate. This process at most doubles the number of variables and does not change the binary length of the Boolean expression itself. So that will change the computational cost parameter n at most linearly, and thus cannot affect the computational complexity beyond polynomially. So it is the message here, it's no loss of generality to force this alternation, which is what we've just seen already here by introducing dummy variables to quantify over universally, and what we saw for the co-NP complete unsatisfiability problem by introducing artificial existential quantifiers to quantify over existentially, and this is in general the case. That was my first remark. My second remark that I'd like to make is what I just forgot. Yes, okay, the second remark is about the last quantifier here. Yes, thanks for the last quantifier here, right? What is the last quantifier? The last quantifier depends on the parity of the number of variables, right? So if m is even, then the last quantifier will be a universal one, right? So the universal quantifiers here are associated with the variables of even index, whereas the existential quantifier is associated with the variables of odd index. So if m, the number of variables, is even, then the last quantifier is a universal one. If m is odd, then the last quantifier is an existential one. But again, that doesn't really matter. It's more a matter of terminology than of actual computational complexity, because again, we can always introduce another and append another quantifier of any type, universal or existential, over an additional dummy variable, which doesn't really occur and thus does not matter or change the value of this expression, right? So that's my second remark about the last quantifier. Depends on the parity, but we can easily introduce another variable to change the parity and thus the last quantifier. Good, so let's now look at the recursive algorithm for evaluating this expression. And the algorithm, kind of proceeds in this way. It first plugs in 0 for the variable y1, okay? And once y1 has been fixed to be 0, then the remaining is a Boolean expression with m-1 variables, right? Starting with y2 as only variable. And so we can make a recursive call to the validity of this Boolean expression, quantified Boolean expression with one less variable to determine whether this is true. And then try the same again with y1 fixed to the value 1. Plug in, replace y1 with a constant 1, arrive at a Boolean expression with m-1 variables, and recursively determine the truth of that expression. So so that means we need 1 bit to store y1, right? For the first recursive call, by hypothesis, induction hypothesis uses this amount of memory plus some polynomial overhead. And then try the same again with y1 is fixed to 1. And again, using this amount of memory for another recursive call, because that's an essential, trivial but essential observation here. The memory used in the first recursive call when y1 is fixed to 0, and the memory used in the second recursive call when y1 is fixed to 1 can be reused. So it's the same amount of memory. It's important. There's not a factor of 2. We don't need, well, with respect to running time, we do need twice the time, 1 for the first recursive call and 1 for the second recursive call, because running time add up in these 2 recursive calls. But with respect to memory, the second recursive call does not need additional or new memory. We can reuse the memory made during the first recursive call. Therefore, from the perspective of memory, S for space here, as opposed to time, there is no factor of 2 here, but the factor of 1. So this is you see, I haven't really spelled out the recursive algorithm at all. I haven't even given a recursive mathematical equation for the evaluation, but I've described this all informally, and the only thing you see here rigorously, formally, mathematically, is the cost analysis, the algorithmic cost, namely the memory consumption of this recursive algorithm. And now it remains to solve that, and that's easy to solve that. This is polynomial. The result is polynomial in n. So yeah, because m, the number of variables, is of course always less than n, the binary length of the expression. So recursively evaluating that, as I just explained, leads to an algorithm whose memory consumption we've just designed a recursive equation for. Solving that recursive equation shows that this problem can be solved in polynomial space and thus belongs to P space. Okay, and we've also seen why this problem may not belong to NP nor to co-NP. It does not seem to belong to NP because it also includes these universal quantifiers, which are typical for co-NP, but it cannot belong to co-NP either because it contains the existential quantifiers, which are typical for NP. So this is a problem which is likely to exceed both NP and QP. And actually, we're going to show that it is complete for PSPACE. So we've just seen that it belongs to PSPACE, can be solved using a polynomial amount of memory. But actually, it's a hardest problem in this complexity class NP. Any other problem in PSPACE can be reduced in polynomial time with respect to a notion of polynomial time reduction to this problem. So how does this proof work? This is kind of a another master reduction, right? So this is kind of a counterpart to the Cook-Lemon theorem, but now for this increased and larger complexity class PSPACE. So let me see. Right. So suppose we have an algorithm here mean while plus program that decides the decision problem L, which is supposed to belong to PSPACE, in polynomial amount of memory, specifically in this amount of memory where poly is an abbreviation for some arbitrary but fixed polynomial. And now we need to do a master reduction. We need to design a polynomial time reduction from this arbitrary decision problem about which we know nothing other than that it can be solved in this amount of memory by this algorithm, and reduce that in polynomial time, convert that in polynomial time into an equivalent instance that is of QBF. So that is true, quantified Boolean formal that is true if and only if for inputs of the original problem, for instances, positive instances to L. And to this end, we introduce a very interesting and generic technique, namely we encode the configuration of this algorithm of this while plus program. Remember that a configuration of an algorithm of while plus program is a kind of a snapshot of all the variables of this algorithm, right? So for each of the constant many variables, we record their contents, and we record the program counter of this while plus program of this algorithm, which is one of constant number of bits. And thus everything, the state of the algorithm A is apart from the algorithm itself. The state of execution is kind of stored in this bit vector, whose length is exactly this length, right? Because remember S, the memory consumption, is really just the number of bits that we need in order to store the entire snapshot, the variables. And now let's turn that into a graph and consider all possible configurations. So all possible vectors of these many bits. Well, there are exponentially many such vectors, right? I mean, the vector itself has a polynomial length, but each entry here, each component is 0 or 1, so it's a bit. And so we have 2 to the s possible values, and thus actually at most 2 to the s configuration. Remember, that was our key argument and analysis in showing that the problem solvable in polynomial space can also be solved in exponential time, because if it takes more than exponential time to run that problem, then some configuration must have occurred twice and thus repeat and thus have an infinite loop. So basically the observation that any polynomial space algorithm has at most exponential many stages configuration, that's something we already had before. And now we take that graph with this exponentially many vertices. Some vertices make no sense at all, do not belong or arise from meaningful configurations, not from configurations that can ever occur, but we don't care. We just draw this graph, and actually we don't draw this in reality, but consider a thought experiment. Consider as thought experiment this graph with its exponentially many vertices, where each vertex corresponds to some configuration of this algorithm. And now we introduce edges, directed edges. A direct edge from vertex U, representing one configuration, to vertex V, representing another representation, if and only if V encodes the algorithm's unique successor configuration after the configuration U. Let me say that again in different words. So every vertex of this graph represents a configuration of the algorithm A, bit vector snapshot of its variables. And if U encodes or represents such a configuration, and now let's in our thought experiment, run the algorithm for one more step, then this will result in a different configuration. Well, a different one, because otherwise there would be a loop, right? But anyway, so it's another configuration after executing the algorithm for one step after having resumed the kind of frozen state from U. One step results in a new frozen state V. If this, in this case, we're going to draw a directed edge in our hypothetical graph from U to V. And so that's, in this way, we convert the algorithm A together with its memory bound S into a directed graph. Yeah, that's a directed graph. This graph may have cycles. The algorithm may actually run indefinitely. No, it may not, right? Because the algorithm, as we defined it, must terminate on any possible input. Therefore, this is a acyclic directed graph of exponential size, exponentially many vertices. So this is a directed graph associated with an algorithm that is while plus program A, and associated with a bound S, or the number S, of bits used by the algorithm on a specific input, where we have a designated static configuration of that algorithm. Namely, that's a configuration when the algorithm starts running on some input X. If we have a different input, then of course the variable x1, where the input is presented to the algorithm, will have a different value, and thus the configuration of that algorithm will be a different one. So the starting configuration includes the value of the input, and we have a final configuration when the algorithm stops, and it's guaranteed to stop eventually after at most exponential steps. And this is unique, right? If it is not unique, then we can kind of make some additional. Yeah, I don't want to expand on that. Let's just talk about the unique accepting configuration, the concept configuration where the algorithm stops and says outputs, yes, this input X belongs to L. I give a positive answer that is a positive instance. So here's a hypothetical drawing of such a computation, now perceived from an perspective as a sequence of transformations on configurations. Here's the starting configuration, which depends on the input X. And here's the unique terminating accepting configuration where the algorithm outputs and says yes. And in between, there's this sequence of intermediate calculations, which may be up to exponentially long. Remember, our goal is to express that as such a quantified Boolean expression. And the first thing is, we're going to simply define that the algorithm A accepts the input X if and only if this graph has a directed path from the starting configuration U, which encodes X, to the unique N configuration W of length or using memory at most S, that is of length at most 2 to the S, where G denotes here this graph, which depends on the algorithm and the memory bound. So this is nothing gained here. We have just reformulated the question whether X, the input X, belongs to L, is equivalent to the algorithm A accepting input X, by the definition A deciding the algorithm. Right here, let me emphasize that. So X belongs to L if and only if the algorithm A accepts X, that's the definition. And now we've defined that by this expression. So what's gained here? In order to see whether what is gained, let us try to express this letter expression using Boolean expression. So this is not Boolean here, but let's try to express it in Booleans. Yeah, something we have also expressed, for example, independent set as Boolean expressions. And now we express kind of the reachability problem for this graph of exponential size. Right, so this is a graph with exponentially many vertices, and we have here directed reachability problem in this exponential size graph, and we want to express that as a Boolean expression. That's what we do here. First, informally saying that there exists a path of length at most 2 to the n, right, from U to W. Okay, so this is again just reformulation, nothing gained here. Also, it's very informal, that's why it's put in this quote. Now let's get this a little bit more formal by saying that there exists an intermediate vertex. That's an important observation. If there exists a path from U to W of length at most 2 to the S, then there must be some vertex on this path let's call that vertex V, some intermediate vertex, which has distance at most 2 to the S minus 1 from U, half the distance, and which has also half the distance from V to the target W. We say that again. If there's a path from U to W of length 2 to the S at most, then there must be an intermediate vertex at halfway between U and W, a vertex whose distance from U is at most 2 to the S minus 1, and whose distance from V to W is also at most 2 to the S minus 1. Does it make sense? Right? And that's an equivalence, right? So if there's a vertex halfway, then that means that the overall distance from U to W is at most the sum of the two distances from U to V and from V to W, which is by induction hypothesis at most 2 to the S minus 1. So this is indeed an equivalence, and it's Boolean, right? So that looks good. Here, if we continue expressing this, yeah, that's kind of an induction step. We've expressed this informal condition, which is equivalent to whether X belongs to L or not, using this hypothetical expression. And now we've been able to expand that using existential quantifier and using a Boolean connective. So by continuing this, replacing this and this, inductively in this way, one arrives at a purely Boolean expression, right? A purely Boolean expression, namely when S is equal to 0, then that means there's one step, there's a path of step 1 of length 1 from U to V, which basically means that V is the next step after U in the algorithm's execution. And remember, according to the Cook-Levin theorem, a single step can be expressed as a Boolean, large Boolean expression satisfiability. So it seems like we're all done here, but let me point out two difficulties here. First, the way we've constructed this Boolean expression PG only uses existential quantifiers, right? So if we spell out this here and replace this, that will introduce another existential quantifier. This will introduce another existential quantifier. And if you continue doing that, we arrive at the Boolean expression using only existential quantifiers, which is by itself is not a problem, but it doesn't seem to really use the power of QBF, where it also provides the use of universal quantifiers and existential quantifiers only. This seems more like a problem in NP than in QBF. That's one problem, which doesn't seem too serious for now. But the second problem is, if we now analyze the number of these quantifiers and the length of this expression after we've really spelled out the recursive definition here and replaced everything with quantifiers so that all variables are now quantified over, right? So here we have a mid vertex, which is accidentally quantified over. And the next step, there's a mid vertex here between U and V, and there's a mid vertex between V and W, gain of half the distance. So when proceeding from S in the induction step to S-1 to the induction hypothesis, the number of quantifiers doubles each time. So we have here 1 in the first step. Next, we will have 2 more. In the next, we'll have 4 more. In the next, we have 8 more. And so when S actually reaches 0, we have actually 2 to the S-1 variables and quantifiers over, which means this expression will have exponential length, exponentially many quantifiers. So, and that's bad. Why is that bad? Because remember, we're trying to reduce the decision problem L to a problem in this form. And we want to do that in polynomial time. We want to construct a polynomial time reduction in order to show this problem, the QBF to be PSPACE complete, a polynomial reduction from L to QBF master reduction. But this is not a polynomial time reduction we've seen here so far, because the output QBF expression has exponential length. And as I said, not only exponential length, but it also doesn't really make use of the universal quantifiers here. So no universal quantifiers, exponential length. This doesn't seem like a good approach in order to arrive at this reduction. Yeah, so I deliberately show you also the dead ends in proof attempts so that you can learn something. So now you can see how we'll see how we fix that both problems. First, that the reduction outputs a Boolean expression of exponential length with exponentially many variables quantified over, and also uses only existential quantifiers rather than universal one. And this is the answer, this is the solution. Namely, we replace this conjunction by a disjunction and another universal quantifier. So the intuition here is that existential quantifiers are kind of like a disjunction, a huge disjunction, big OR, right? First possible value for V, or second possible value for V, or third possible value for V. Well, exponentially many possible values as witnesses, right? And similarly, conjunction is a special case of a universal quantifier, but here we have only a binary conjunction, whereas the universal quantifier can range over in this setting over up to exponentially many. But that's okay. We use a binary one in this way, use two binary universal quantifiers to equivalently express that expression with its two, you see there are two recursive calls when expanding that until s reaches the value 0. And here's an equivalent lay where there's only one kind of recursive structural recursion to the expression of with the parameter s minus 1, namely 1, which is actually equivalent. So let's look at that and discuss that. So first part is the same, existentially quantified over V. And then instead of saying the first part from U to V, length at most 2 to the s minus 1, and from V to W to this, we say from S to T in length at most s 2 to the s minus 1, that's a discrete s. And then we say that either s is equal to U and T is equal to V, in the first case, or s is equal to V and T is equal to W, the second case. So we kind of express this and use these complicated expression with universal quantifiers in order to combine these two recursive sub-expression into one, or reduce that to only one recursive sub-expression. You see that here? So let me emphasize that again. So this means either s is equal to U and T is equal to V, or s is equal to V and T is equal to W. These are the two cases to consider here. And these cover exactly these two cases by introducing new variables and introducing universal quantifiers. So this is indeed equivalent. But now when we spell out this inductive definition of this expression, instead of this one, they are semantically equivalent, but this leads to different syntactical expansion. Now replacing this s minus 1, applying the same again, introduces one existential and two universal quantifiers and reduces the parameter s by one more down, and repeating this until s reaches 0, thus results in a Boolean expression whose length is only polynomially. So it's an equivalent, semantically equivalent to when we expanded that expression. But syntactically, this one is much shorter at the expense of using and introducing universal instead of just existential quantifiers. So to summarize, when expanding that, one arrives at a quantified Boolean expression which uses both existential and universal quantifiers, having polynomial length. Polynomial in S, the number of bits, S, remember this parameter, which expresses, let's say it's semantically equivalent to that, semantically equivalent to that, semantically equivalent to that, which is semantically equivalent to X, the input belonging to L. So this expression is now expression of this form, and it's semantically equivalent to whether X belongs to L, and thus satisfies the two conditions of the polynomial reduction, namely for positive instances X, this first expanded expression with the quantifiers is true, and vice versa. If this is true with all its expanded quantifiers, then X must belong to L. And the third condition is that the polynomial, that the reduction is computed in polynomial time, and that's what we took the second approach, because the first led us to a dead end with respect to polynomial time. It was still equivalent, so the other two conditions were met here, but not a polynomial time, whereas this one can be computed in polynomial time, and this concludes a proof of the polynomial time reduction, mass reduction from an arbitrary decision problem in PSPACE to quantified Boolean expressions. So Yeah, so that concludes the proof of PSPACE completeness of this problem. And yeah, how to summarize that? So here in this polynomial time reduction, I have not really spelled out the first step in a polynomial time reduction, namely to specify the reduction fully. We've specified the reduction function, the translation function, as the result of an induction, right? Actually, as in our first attempt, we tried one inductive construction, which didn't turn out to not be feasible in polynomial time because it turned out to have exponential length. And then we tried another construction, which is semantically equivalent, but which in the induction step spelled out leads and yields a output expression whose length is finally polynomial. So yes, that concludes our proof. And let's now consider a variant of QBF, namely 3QBF. So 3QBF is the same, but with the additional condition that the part which is not quantified, the part which is quantified over the quantifier 3 part here is in 3 conjunctive normal form. So that's another observation. So with QBF in general, this is just an ordinary arbitrary Boolean expression in the variables with the out quantifiers. And now we consider this to be a Boolean expression which is in a special form, namely a 3 conjunctive normal form, that is a conjunction of disjunctions, where each disjunction, each clause has at most 3 literals, that is variables or negated variables. And we already saw that this can be achieved with another reduction by possibly introducing new variables. Remember our reduction from 4 satisfiability to 3 satisfiability. In more general, our polynomial time reduction from satisfiability to 3 satisfiability. And the same can be done here by introducing possible new variables to be quantified over existentially, but at most linear number of new variables with new existential quantifiers, and then possibly introducing inserting additional universal quantifiers in between, just to force this alternation dummy variables. So long story short, quantified Boolean formula as a decision problem is polynomial time equivalent to 3 quantified Boolean formula, namely the truth of such expressions with alternating Boolean quantifiers, where the quantifier 3 part must be in 3 conjunctive normal form. This, or put differently, requiring the quantifier 3 part to be in 3 conjunctive normal form does not change the computational complexity at all, like moving between 4 quantified conjunctive normal form and 3 conjunctive normal form does not affect the computational complexity more than a polynomial either. And yeah, I don't want to spell out this reduction from QBF to 3 QBF in detail. It's basically the same. You already know the techniques that we've seen previously, and I'd like to make this as a kind of a homework assignment, spell it out in details, not mostly for the purpose of your own understanding. Just a second. So, right. What is this 3 quantified Boolean formula decision problem good for? Since we've explained that it is polynomial time equivalent to the previous one, that it means that it is also PSPACE complete, right? yeah, it's equivalent to QBF without the 3 conjunctive normal form condition, which we've just established to be PSPACE complete on the previous slide. So 3 conjunctive Boolean formal is also PSPACE complete. And so we have already 2 PSPACE complete problems now. And the next problem, here you see PSPACE complete. And now we want to introduce a third PSPACE complete problem. And that's going to be a game for 2 players on some directed graph. So let me introduce that decision problem, but first introduce the game. Consider an arbitrary, directed graph with 1 designated start vertex. Here you see an example. This is a directed graph. Maybe have cycles. Doesn't even need to be connected, but it has 1 designated vertex, the start vertex. Okay, and the decision problem is the following, or the game is the following. We have 2 players. One has blue pebbles or markers, and the other player has red pebbles or markers. And initially, the graph is empty except for the designated start vertex where a blue marble, a blue pebble is placed. And then alternatingly, now the red player's turn is to place a red pebble on a vertex which can be reached from the current blue one. So in this example, this is just one example graph, but you can imagine, and I really would like you to imagine any other directed graph. And now let's put a red pebble on some successor of this blue pebble, namely this one or this one. These are the 2 possible successors because they are directed arrows from here to here or from here to here, directed arrows. And so let's just suppose, for the sake of an example, that the red player puts a pebble here. Now it's the blue player's turn again to put a pebble on a successor node, successor to this red pebble. In this example, there's only 1 possible successor, namely this vertex, right? Oh, there's again the noise. Right, this is the only possible successor because this node is follows the edge in the wrong direction, and same here. So now actually the blue player has only 1 choice left, right? So the red player's move, putting the pebble here, has forced the blue player into only 1 possible option, namely this one. Okay. I'd like you to also consider, like in the game of chess or in the play of Baduk, the other, what would have happened if the red player had chosen this vertex. But let's continue with this choice. Now it's the red player's turn again to put a red pebble on a successor node to this blue pebble. And the red player now has 3 choices, this one, or this one. And let's just suppose, for the sake of example, that the red player chooses this one. Then it's the blue player's turn again. And the blue player again, gosh, now maybe we see why the red player has chosen that particular move as opposed to the other 2, because now the blue player again only has 1 possible choice, namely to put a pebble here. Then it's the red player's turn again. The red player has 2 options, this one or this one, right? Let's say the red player puts the pebble here. And now it's the blue player's turn, and the blue player has no option left because the only successor node is this one, and this is already occupied by a pebble. As a matter of fact, by a red pebble, but it doesn't really matter. What matters is that any successor node is already occupied, and in the game it's prohibited to remove pebbles, only placing pebbles is permitted, infinite supply of pebbles. And so the baseline is the blue player has no move left anymore. Previously, the blue player had only one possible successor move, and now not even that. The blue player has 0 successor move, which means that now the game is over and the blue player has lost and the red player has won. So these are the rules of the games and an example run of this game for a given directed graph with a designated start vertex, which is marked in blue. Okay, and you see how this is a game for 2 players to play, like I mean, there are many 2-player games like tic-tac-toe or Baduk or chess. And this is another 2-player game. How does that amount to a decision problem? The decision problem is the following: given such a directed graph with the designated vertex already marked in blue, does the player have a winning strategy? So let's write that again. So we have a directed graph with a designated start vertex. We have the rules that alternatingly the red and the blue player place pebbles in their respective color onto the nodes following, always following the edge, one edge in the designated direction, mark the current vertex, and then follow an outgoing edge to a yet unmarked vertex. If the only unmarked vertices are permitted to have a pebble put on, and when a player cannot make such a move that follows an edge to an unmarked vertex, then that player loses and the other player wins. These are the rules of the game. And you can imagine this game for any possible directed graph with designated start vertex, right? And we say that red has a winning strategy if, however blue reacts to red's move, red can follow up with a move so that however blue reacts, red has another follow-up move, so that however blue moves, red has another follow-up move, and so on until in the end blue loses. That is a winning strategy for red. Let me say that again. A winning strategy is something where blue has no possibility at all to win, provided that red plays optimally. Yeah, maybe that's a good way of phrasing it. A winning strategy is an optimal way of moving for red. Optimal in the sense that whatever blue does, again, there's an optimal follow-up move for red, and so on until in the end blue loses. That's a winning strategy for red. Similarly, you can consider winning strategy for blue. What is a winning strategy for blue is, however, that blue proceeds in a way such that however red reacts, blue can follow up such that however red reacts, and so on. In the end, red wins and blue loses. Blue wins and red wins loses. And it seems kind of immediate or intuitively obvious that red has a winning strategy if and only if blue has no winning strategy, or put differently, either red has a winning strategy or blue has a winning strategy, but not both nor none. And that's intuitively should be clear, but actually formally and rigorously, this is more subtle. And actually, it really depends on what is called a compactness property here. It basically means amounts or boils down to the fact that each player has at most finitely many choices at each stage, and that the length of the game is at most finitely long. Why is that true? Well, because it's a finite graph that we start with, right? A finite graph means every vertex has at most finitely many successor vertices. And during each move of the game, precisely one vertex gets occupied by a pebble, either red or blue one. And since initially there are at most finitely many vertices to begin with, after at most finitely many steps, all vertices will be covered. That's the worst that can happen. So this is a finite game, as I say, and it's a finite game without draw. So either blue wins or red wins, but there are no draws. And these kind of games have this duality that they either red has a winning strategy or blue has a winning strategy. Whereas there are some famous examples, counterexamples in logic of infinite games where neither player has a winning strategy, neither red or blue. But that's a very interesting but different topic. So long story short, yeah, this game has a winning strategy. Yeah, if I might digress here, also chess is a finite game. Why is it finite? Superficially, it's not, because one can repeat a move, right? But then there's this rule of chess: if a configuration gets repeated, then the game ends. And this is what makes chess a finite game. And it's an open question how to optimally bound that number, the size, the game. And follow-up problem, open. Who has a winning strategy at chess? Is it black or is it white? The theory says that precisely one of the two has a winning strategy. Now, of course, if one could solve that question, maybe even better, determine a winning strategy, then the whole game would kind of be solved. There would be no point left in playing chess, nor by human players, nor by a computer. But although chess is finite, it is so incredibly large and, in a sense, unstructured that nobody really knows. There's some conjecture that the starting color of chess has an advantage and therefore maybe has a winning strategy. But this is all just intuitive guessing, and there's not really rigorously known. Okay, so much about chess. I've recently been watching Queen's Gambit, the TV series, and that spurred that kind of digression. Thanks for indulging me. So to summarize here, we have a finite game. Precisely one of the two players has a winning strategy for every given graph. And the decision problem associated with the graph is, given the graph and given a designated start vertex, is it red who has a winning strategy? So now this, after all I've explained, this is a decision problem, a yes-no problem. And observe that it is well-defined. That's what I've just explained, because precisely one of the two players has a winning strategy. And if it's red, then we say the decision problem should say red, and otherwise it should say blue, or put differently, should say yes or should say no. So this is a decision problem. And since time is up, next time we're going to show that this decision problem also can be solved in polynomial space, polynomial amount of memory. Given the graph with start vertex, does red have a winning strategy? Yes, no. And then this decision problem is also PSPACE complete. And we were going to design a polynomial time reduction from this game. Polynomial time reduction from 3 QBF requantified Boolean formula to this game. So to summarize, today we talked about this larger complexity class PSPACE. We've discussed some problems in this complexity class, specifically quantified Boolean formula and 3 quantified Boolean formula. We've shown the first to be PSPACE complete And we've mentioned that this polynomial time equivalent to the 3 conjunctive normal form restriction. And finally, we've started talking about decision problem on graphs for 2 players, which will next time show to be also polynomial time complete for this complexity class. Thanks for your attention. That's all for today. And yeah, see you next time.